Hi everyone. Yeah, thank you for joining today. My name is Inge Nieuwoud and I work at a company called BioEnergy Netherlands, where we specialize in converting wood biomass into two valuable products, namely green molecules and biochar. Today, I'll focus a little bit more on the biochar side, which I think is especially relevant for this series, but I'll also touch on the energy and carbon capture aspects of our work. Also joining on the call today is our company CTO, Phil Levison, if you have any in-depth questions afterwards. But before starting to explain who we are, I would like to start by stating our whys. Why are we specifically focused on green molecules and not just energy generation? And why is this technology so important towards our goal as a fully circular economy? And why specifically biomass gasification? Sorry, this slide, there you go. If you have a look at the assessment report from the Intergovernmental Panel over here, let me just get my laser pointer, then you can see the global surface temperatures projection on the left-hand side for different scenarios in the future. This is where we're at the moment. This report basically discusses the current state, the future climate change, risks, and long-term results of climate change. It clearly indicates that the rise in global temperature will cause elevated risk scenarios for society, showing that we must rapidly shift away from fossil fuels, and that carbon removal is an essential part of the challenge to limit the global temperature rise to 1.5 degrees Celsius. This is here shown in the light blue shared socioeconomic pathway. So the biggest challenge of the energy transition is finding sustainable alternatives for fossil fuels and resources. As a company, our mission is to step into this gap of replacing fossil fuels by producing green molecules such as green hydrogen and green carbon dioxide. This is to be used as a resource in the chemistry and for transport fuels. We aim to do this by making use of local and sustainable residue biomass flows. So who are we? This over here is our patent in our technology, as you can see, the gasifier. So from here, we produce two products, namely syngas and biochar. The biochar that we make is an almost pure form of carbon that sequesters carbon dioxide and has several advantages, including soil enhancement, and therefore we're completing this biomass cycle. Then we also have our syngas, which is a mixture of several gases, mostly hydrogen and carbon monoxide. And from here, you can actually separate out pure green hydrogen, as well as green CO2 for the usage in the horticulture, as well as the storage of CO2. Furthermore, you can also upgrade the syngas to SNG, LNG, biomethanol, ammonia, and even sustainable aviation fuels, or SAF. So if gasification is so wonderful and versatile, why is it not that well known yet? The history of gasification goes quite a long time back, up to the 19th century, but its development has faced several and recurring technical, economical, and operational challenges. The most significant historical challenges include star formation, but you also have high moisture content in your biomass, ash and clinker formation, and reactor and design limitations, maintenance and reliability issues, increased downtime that adds to capex and opex due to these stars. And it's important to note that TARs within the gas makes the gas not suitable for engines or for catalytic upgrading to higher value products. So this is just to show our technology and putting it in perspective. Like I've mentioned before, traditional gasification approaches has a really high tar content of usually around 5,000 parts per million, while our technology tar content lies around 10 parts per million. This results in a massive reduction in the maintenance cost and making this gas suitable for catalytic upgrading without heavy cleaning steps. For our mission, it is very important for us to vet our supply chain very closely to ensure that we use sustainable biomass to reduce our global CO2 emissions. It's very important to understand that we really do not burn biomass, but we rather gasify it without enough oxygen to actually ignite. So the type of feedstock that we usually operate on is forestry waste, sawmill waste, A wood, B wood, as well as RDF pellets. All of the feedstock that we use is the NTA 8080 certification, and it is also RED II compliant. So even though we have conducted tests on B wood, we do prefer forestry wood, sawmill, and A wood due to it being very clean, and it causes a really high quality biochar that it can then again be reused within the soil to complete the biomass cycle that I've shown previously. So looking at the technology overview, you can nicely see the flow of the carbon, the hydrogen, and the oxygen molecules. During the gasification process, the wood chips and the preheated air continuously enters at the top of the reactor. Our gasifier is a downdraft stratified gasifier, and it produces just two products, namely syngas and biochar. The gasifier consists of two zones, namely the upper zone and the lower zone, which is divided by gasifier grades. Below the grade, the syngas is separated from the biochar and removed from the reactor in different streams. The whole gasification process is based on zero-point clean tech technology called the zero-point gasification process. The controlled reactive zones within the gasifier, together with the higher operating temperatures when compared to traditional pyrolysis process, is what results in these cracking of the tars and a lower tar quality within the syngas. So here you can actually see our facility on the right-hand side. That's one of our generations of the gasifiers. And on the left-hand side is the other line. And here you can also see the gas analysis over a day of operations. So within our syngas, our CO is around 22% and our hydrogen around 18% of our syngas. Next, you can see the process flows entering and exiting our reactor. We consume around 7.7 nomical cubes of wood chips on an hourly basis, and this results in 3,500 nomical cubes of syngas and 50 kilograms of biochar per gasifier. The density of our biochar is quite low, as you can see, at 100 kilograms per cube. So this 50 kilograms per hour is around half a cube of biochar and around only 3% on weight basis of our feedstock. Our facility is an at-scale R&D facility here in the Amsterdam port area, with two of these lines that I've showed before installed. So our technology is scaled on a modular basis, meaning if you want to increase your plant throughput, you actually put more of these production lines. And this also includes the reliability of your system, making it more flexible for maintenance planning, etc., while still reaching your 8,000 uptime on an annual basis. So here you can actually see our reactor, our heat exchanger for heat recovery, as well as our scrubber systems for removing finer dust particulates. From here, we use only established technologies and well-known partners to create high-end products from our syngas. For example, I can give is last year we actually separated out pure biohydrogen together with our partner Highgear, using already existing technologies. So looking at the overall picture, we as a society has several well-known technologies available for carbon positive energy, as well as some carbon neutral solutions, including water, wind, and solar. But what we're trying to do is taking this one step further by not only storing fixed carbon in the form of biochar, but also separate and utilize the CO2 from our process, becoming a carbon negative solution. We are therefore a bioenergy with carbon capture and storage technology. This is also otherwise known as BECCS. So for determining the quality of our biochar, since we're based in the EU, we've decided to use the process of the EBC. So we've started this process last year to register our biochar with the EBC. And through this process, we've done an analysis on our biochar, and you can see the lab results of this test, with our carbon content around 90% of our biochar, ash around 5%, and our biochar has a really high porosity and high surface area that's really great for water holding capacity. And here you can see what our biochar would typically look like. So after completing the full process of registration, our biochar has received certification for both the EBC Agro-Organic as well as the EBC Feed Plus. proving that our biochar is safe for the soil as well as animal use. So one of the requirements were also to complete the life cycle analysis for our biochar. This was done by external company, and they came up to this figure of 2.8 kilograms of CO2 per kilogram of biochar that we produce. So that's the CO2 that's sequestered. And this is the number that you can then use in order to calculate your carbon credits that you can sell in the carbon credit market. So for our market research, we started off with the typical applications of the EBC. This includes within the agriculture for soil fertility and water retention, biochar as a feed additive for animal health and reducing emissions, and looking into other applications for construction materials as well as sustainable steel production. So over the last year, we've received our EBC certification and we've been part of several research projects. This included looking into the EU-based horticulture to the future. Through Wageningen University, we're looking into biochar as part of a mixture for a circular fertilizer. And later this year, we'll also want to start looking into biochar as a sustainable growth media within the horticulture sector. On top of that, we're also involved with two master studies. The first being looking at the impact assessment of biochar on sediment ripening, and the second investigates biochar salt hydrate composites for heat storage. So it's a lot of different types of studies that we're looking into at the moment. Then the first project that I would like to show is the circular fertilizer research project with Wageningen University. So the objective of this project is to solve bottlenecks in the transition from mined and specifically energy inefficient fertilizers to the use of circular organic fertilizer. For this project, we're part of a much bigger consortium, including potting soil suppliers and fertilizer suppliers. We have supplied the biochar to this growth test, and here you can actually see the peppers that's grown out of this fertilizer mixture, with I think around 10% of our biochar. Further, we also have a master's student at Delft University completing research on assessing the impact of biochar on sediment ripening, specifically examining how biochar particular size and amount added influences the soil's organic, biological, and physical properties. This is part of the general goal of accelerating sediment ripening and improving the properties for earthen construction, such as dikes. So some key highlights from her study, like I mentioned before, it's part of a much bigger project called Sediment to Soil. And these experiments are conducted in Delft with using sediments from Hamburg. And the goal is to improve the soil water holding capacity, reduce its shrinkage, and stabilize the organics. The summary so far of her study has come to that biochar added showed physical analysis that you have then a lot more reduced shrinkage behavior, you have increased moisture content and water holding capacity, and the chemical analysis showed to increase pH. And the last, I think most important one is biological analysis showed to reduce CO2 emissions. Then next, we also have a master student completing his studies assessing biochar salt hydrate composites for heat storage. First, he chemically upgraded our biochar to a surface area of over 1,300 cubes per gram. Then he impregnated the salt hydrates, like you can see over here, into the biochar. And after this, the composite was tested over several cycles by hydrating and dehydrating it to test its stability. And some key highlights from his study so far is that this biochar matrix supports salt hydrates. It enables that you can do repeated hydration and dehydration of the salt, efficiently stabilizing the reaction. And that means that biochar is a promising composite for all kinds of absorption applications, including heat storage with thermochemical salt hydrates. And here you can see the same of our biochar with the nice little veins over there. So this is where I would like to end for today, that we still have some time for questions. Feel free also to reach out after the webinar. You can see my email over here or our site, that you can learn a little bit more about our biochar, our gasification process, or our future plans. Thank you.
Thank you very much, Inge. Very interesting to see the surprisingly large pilot plant. I thought it's smaller. So the floor is open for questions, and you got one from Christian, who was asking. So thanks for the specifications on the biochar. I have one more question. What is the percentage of pH 8 or pH 16 in the produced biochar? So did you check the pH content?
Yes, we did. For this specific one, it was 8, I think.
8 milligram per
The pH, right?
PAH. So
Oh, PAH.
yes.
Yes, yes. Sorry, but I do not know that from the top of my head. But it's in the analysis. It's also the same analysis sent to the EBC. So that
And,
falls within their agro-organic limits. So I think
okay.
that's around 4, less
Yes.
than 4. Yeah.
Yeah. So it must be less than 4. Yeah.
Yes. No, it's approved by them. So it's within the agro-organic as well as the feed plus. So whatever they have, it's less than that.
Um, which is actually quite good because usually gasification trials are horrible. So Paul
Yeah.
Anderson was asking, can you comment a bit about your cost structure? I would also be very interested in how much you want for your biochar actually, or what's the price that comes out of your biochar as a byproduct?
Currently, we're looking at 150 euros per cube. So for our biochar, I know in the Netherlands we're the only people registered with the EBC. There are obviously other suppliers within the Netherlands, but as biomass is not that widely available as it is in Germany and Austria, there's not that many gasification plants here.
Yeah.
So our biomass is mostly from sawmills, so their waste.
Hmm.
They chipped edges of the wood that they use in the sawmills. That's mostly what we get for our feedstock.
Hmm.
But as a supplier, we're looking at 150, like I said before.
And because that's also another specific for gasification, how what's the particle size requirement for your process to be working? So I guess it's
We're
limited.
For the feedstock, we're between 5 millimeters and 50, but one of our R&D projects is also to increase that size to 60.
Okay.
So to be able to use the larger feedstock, because our limitation is not always the size, it's more the shape.
Hmm.
We can definitely gasify bigger wood chips, but sometimes if they shred the wood chips, the stringy parts make basically a mat, and it's difficult for our conveyors to move that around then. So it's
Okay.
not necessarily on the reactor, but how our system is laid out, we do need more uniform feedstock size compared to the shredded feedstock.
Okay. And you can use pellets. You mentioned that you can use RDF pellets.
Yeah, so when they did the initial test, they also did test on that. I was not involved with that, but
Okay.
that is also usable as long as it's heat pressed.
Okay. So you was asking sediment to soil. What is the origin of this sediment, if you know
It's
that?
from Hamburg within the, you mean the region or the origin?
The origin.
Origin, it's within Hamburg in the port area, as far as I understand. So they have a lot of sediment there that they can't use for anything else, and they need to actually have it back. They want to see if they can make soil out of it. So it's an overall project including Wageningen University, sorry, Delft University and Hamburg.
Yeah.
So it's a collaboration between the two universities.
So I assume that answers the question. I'm not sure. Um, Samsarin was asking, what is the cost of the hydrogen you can produce at scale?
The hydrogen you have to, so we've separate out 10 cubes per hour. We can separate out a lot more. So we still need to do a cost analysis for that, exactly how much that will cost. But if they send me a message afterwards, I can also just send them that results because I also don't know on top of my head
Yeah.
the exact number because we do have models for that, how much relatively that will cost.
Okay. Um, and and the general question, I think, can you use anything else than wood?
I think if Phil are you in the call?
Um,
Sorry, the CTO.
Yes,
yes,
I am. Sorry,
Yes,
guys.
I feel.
he's the technology side. Hi.
I feel. So any other feedstocks than wood? Is it possible
Yes,
in theory or?
we tested a whole range of feedstocks, and they're all applicable. And we mentioned RDF and things, and also agricultural waste and woody biomass is fantastic, but it can be an off product of woody biomass. So, but anything, the whole range of biomass is more or less has the same chemical composition and the same performance in the gasifier. It's, as Inga mentioned, it's more the shape of the pellet or the briquette going into the gasifier that's important.
Okay. Okay, so but I guess you haven't tried something like animal manure or sewage sludge, or did you?
It gets trickier, and then we have to start diluting with wood chips, to be honest.
Okay.
So there are blends. 100% not, but it's possible.
Okay.